Hello, everyone, and welcome. I'm excited to have you here today. We're about to dive into the foundations and applications of supervised machine learning. The focus will be on understanding the algorithms, models, and how we can practically implement these techniques for predictive analytics. Over the next few slides, we'll explore what makes supervised learning powerful and how it can be applied across different fields. So let's get started. Welcome to an overview of the course structure and logistics. In this course, we'll explore the foundations and practical applications of supervised machine learning, covering both theory and real-world use cases. You'll learn about key techniques like linear models, decision trees, neural networks, support vector machines, and deep learning. We'll focus on understanding not just how these algorithms work, but why they work, emphasizing the mathematical concepts behind them, such as maximum likelihood and regularization. This approach helps deepen your comprehension of the principles driving machine learning techniques. The course is designed as a reverse classroom, meaning you'll have access to pre-recorded lectures online before our weekly sessions. These sessions will be dedicated to discussions, homework, and tutorials, really reinforcing what you've learned and giving you hands-on experience. In terms of prerequisites, you'll need some programming experience, preferably with Python, along with college-level linear algebra and probability. But don't worry, no prior machine learning experience is necessary to enroll. All course materials, including slides, detailed notes, and lecture videos, are freely accessible online. Plus, you'll have executable Jupyter notebooks that let you practice coding and see algorithms in action, making the learning process more interactive and engaging. Supervised learning involves three key elements: a dataset, a learning algorithm, and a predictive model. These components work together to enable us to make predictions based on input data. For example, one common application is predicting diabetes risk from a patient's body mass index, or BMI. This example helps illustrate how real-world problems can be tackled using machine learning techniques. The dataset used in this process typically consists of patient BMI values paired with their corresponding diabetes risk scores. This data forms the foundation for training our predictive model, allowing it to learn patterns and relationships. In terms of implementation, Python plays a crucial role. For instance, we can load the UCI diabetes dataset, isolate the BMI data, and then visualize the relationship between BMI and diabetes risk. Usually, the visualization clearly shows that as BMI increases, so does the risk of diabetes, which helps us understand the underlying trend. Finally, the supervised learning workflow itself involves collecting data, training the model, and making predictions. This process is essential because it enables us to build models that can generalize well to new, unseen data, ultimately making our models more useful and robust in real-world applications. In this slide, we're diving into the components of supervised learning algorithms, which are fundamental to how these models work. First, we have the optimizer, which searches for the best parameters, typically represented as θ0 and θ1, that fit our training data as closely as possible. The goal here is to minimize an objective function, often called a loss or error function, to reduce prediction errors and make our model more accurate. To do this efficiently, we often use libraries like scikit-learn, which help solve these optimization problems cleanly and quickly. Visualizing the process can be really helpful, so imagine plotting different candidate lines on a graph to see which one best captures the data trend. The optimizer then selects the final line, or model, that fits the data best. Next, we have the model class, which is essentially the set of possible functions our algorithm can choose from. Think of it as defining the form or structure of the relationship we're modeling. For example, a simple linear model that relates BMI to diabetes risk. Mathematically, we write this as y equals θ1 times x plus θ0, where is BMI and y is the risk. This gives us a clear, mathematical way to express the relationship between the input and output variables. Overall, these components, searching for optimal parameters, minimizing prediction error, and defining the types of models, are all interconnected. They form the foundation that allows supervised machine learning to make accurate predictions based on data. Now, let's look at how we train our linear model using scikit-learn's linear regression. We apply it to the training subset of our diabetes dataset. After training, the model calculates the best fit parameters, which in this case are a slope, or θ1, of approximately 37.38, and an intercept, θ0, around minus 797.08. These numbers tell us how BMI relates to the predicted diabetes risk. Moving on to interpretation, we see that higher BMI values are associated with higher predicted risks of diabetes. This positive correlation makes sense, as we would expect greater BMI to increase health risks. To visualize this relationship, we overlay the fitted regression line onto a scatter plot of the training data points. Doing this helps us visually confirm how well the model captures the trend, essentially, whether it fits the data nicely. Indeed, the regression line aligns with the data points, clearly showing a positive trend between BMI and diabetes risk. This visual confirmation is crucial because it demonstrates the model's effectiveness in capturing the underlying pattern. Finally, from this model, we gain key insights. It provides a straightforward, interpretable picture of the relationship between BMI and diabetes risk. Plus, it highlights the predictive power of linear regression, especially in medical datasets where understanding such relationships can be vital. Now, let's look at how supervised learning models can make predictions on new, unseen data. This slide highlights the concept of generalization, which is really key in machine learning. It's about how well the model, after learning from training data, can apply that knowledge to predict outcomes for new examples it hasn't seen before. You can see here that the model successfully uses the patterns it learned to make reasonable predictions for new patients, even if they weren't part of the original training set. Moving on to prediction accuracy, the model does quite well, correctly identifying patients at higher risk, which is crucial in a healthcare context. While it might not be perfect for everyone, its ability to distinguish higher risk levels demonstrates its reliability and practical utility. The visualization on the slide helps us understand this better. The black points are the training data, the red circles are new patients, and the red crosses show the model's predictions. This visual comparison allows us to see at a glance how well the model is performing, where it's getting it right, and where there might be room for improvement. Finally, let's talk about how the model actually makes these predictions. It uses a simple linear equation based on BMI values. Essentially, it takes the BMI of a new patient, multiplies it by a learned coefficient, and adds an intercept to produce a risk estimate. This straightforward approach makes the model transparent and easy to interpret, which is important when applying machine learning in real-world scenarios like healthcare. Now, let's look at some key applications of supervised learning that really demonstrate its power. One exciting area is object detection in autonomous vehicles. Here, the system learns from labeled examples, meaning it's trained on images where objects like pedestrians, other cars, and traffic signs are already identified. This allows self-driving cars to recognize and respond to their environment accurately, ultimately enhancing safety and navigation. Another important application is language translation. Supervised learning helps machines convert text from one language to another by learning from paired sentence datasets. This structured data enables the system to produce high-quality translations, making communication across languages much smoother. In the medical field, supervised learning is used for tasks like medical image classification. For instance, predicting the severity of a tumor relies on labeled images, so the model can accurately identify and assess medical conditions. These models depend heavily on well-labeled datasets to ensure precision. Finally, let's talk about the predictive power of supervised learning. As we gather more data, these models can often outperform even human experts. They help us understand how input variables, like BMI, affect outcomes, such as diabetes risk. For example, a positive slope in a graph indicates that as BMI increases, so does the risk of developing diabetes. This ability to predict and interpret relationships is a major strength of supervised learning and underscores its importance in many fields. Now, let's take a closer look at the diabetes dataset overview. This dataset includes data from 442 patients, and it features 10 different numeric attributes. These attributes include age, sex, BMI, blood pressure, and 6 measurements related to blood serum. Each data point, or training example, is a pair consisting of a feature vector and a target value. The feature vector, which we denote as x to the power of I, contains the patient's attributes, while the target, y to the power of I, indicates their diabetes risk. To make the data more consistent and comparable across different attributes, the dataset has been normalized. This means that each feature has been scaled to have a mean of 0 and a standard deviation of 1, adjusted by the sample size. This normalization is important because it helps us avoid biases that could arise from attributes having different scales or units. When we talk about dataset notation, we use the symbol D to represent the entire dataset, which is a collection of all these pairs. Specifically, D contains pairs of the form x to the I, y to the I, for I from 1 up to n, where n is the total number of examples. In this notation, each input vector x to the I is an element of r to the d, meaning a d-dimensional real vector, and the target y to the I is a real number itself. Each feature vector x to the I encapsulates all the attributes of a patient in a numeric format, which is essential for building predictive models. And finally, in terms of practical analysis, Python code can be employed to display these dataset attributes and their normalized values. This makes it easier to analyze and visualize the data, helping us understand its structure and properties more effectively. Now, let's delve into the features and attributes in supervised learning. Attributes are basically numerical variables that describe our inputs, like age, sex, BMI, or blood pressure. These serve as the foundational data points that we analyze and use for modeling. Next, we often perform feature engineering, which involves creating new features from these attributes to capture more complex characteristics. For example, we might combine age and sex to create an old man feature. This process is crucial because it enhances our model's ability to understand patterns and make better predictions. Moving on, it's important to distinguish between different types of features. Some are continuous, like BMI, which can take any value within a range, while others are categorical, like sex, which has discrete categories. Recognizing this difference helps us choose the right modeling techniques. We also visualize our data to better understand it. For example, plotting BMI shows us its distribution, and visualizing sex helps us see how categories are spread across the dataset. These visualizations reveal the structure and variability of our data, guiding our modeling choices. Finally, I want to show you a practical example in Python, where we create a custom binary feature, indicating whether a patient is an old man. This example highlights how feature engineering is applied in real-world supervised learning tasks, making our models more informative and effective. Let's dive into targets and problem types, regression versus classification. Targets are essentially the outcomes we want to predict, and they can be either discrete classes or continuous values. If we're dealing with categories, like identifying whether an email is spam or not, we're looking to create decision boundaries that separate these categories effectively. When the targets are discrete, supervised learning problems are categorized as classification. Recognizing whether we're working with classification or regression is crucial because it guides our choice of models and the evaluation metrics we use to assess their performance. Now, focusing on classification, this involves predicting discrete classes. Think of it as assigning labels, such as diseased or healthy. The goal here is to find the best way to differentiate these categories. On the other hand, regression deals with targets that are continuous values. For example, predicting a risk score for diabetes, which can take any value within a range. When we visualize these risk scores, we see a continuous distribution, confirming that this is a regression problem. Instead of separating categories, we're fitting curves or functions to data points to make accurate predictions. Understanding whether we're tackling a classification or regression task, helps us select the right tools and metrics to evaluate our models effectively. Let's take a closer look at how we represent data in supervised machine learning through matrices. The dataset is organized as a feature matrix, denoted as X, which belongs to the space of real numbers with dimensions n by d here. Each row in X corresponds to an individual input vector, xi, which contains all the features for a specific data point. This matrix structure is fundamental because it provides a clear and organized way to handle input data across various tasks. Moving on, targets are expressed as a vector y, which is in real numbers with n elements. This vector contains all the target values, y, I, associated with each input. Using a vector simplifies how we represent output data, making it easier for algorithms to process and learn from the data efficiently. Now, why is this linear algebra formulation so powerful? Well, it allows us to define algorithms more concisely and perform computations more efficiently. It streamlines our workflow and brings mathematical clarity, which is especially valuable when dealing with large datasets or complex models. To make these ideas more tangible, we often work with practical examples, such as extracting feature matrices and target vectors from real datasets like the diabetes dataset. By doing this in Python, we see firsthand how these mathematical concepts translate into actual code, demonstrating their relevance in real-world scenarios. This connection between theory and practice is what makes the mathematical representation so essential in supervised machine learning. Now, let's take a closer look at the formal optimization process in supervised learning. The core idea here is that our optimizer is tasked with solving the problem of minimizing a function, which we denote as j of theta. This j, theta, essentially quantifies the prediction error, how far off our model's predictions are from the actual data. By minimizing this error, we're guiding the training of our model and setting the foundation for evaluating its performance. The optimizer itself is an algorithm that searches for the best set of parameters, which we call theta, to minimize the objective. Think of it as a process that iteratively adjusts the model's parameters to find the most accurate possible fit to the data. When successful, this process results in the most predictive model we can develop given our data and framework. Next, we have the objective function, which is a key component in this process. It measures how well our model is fitting the training data. Common examples include mean squared error, which penalizes larger errors more heavily, or absolute error, which looks at the magnitude of errors regardless of their direction. This function provides a clear metric that guides the optimization process. Finally, there's the model class, which is essentially the set of all possible functions that could map our inputs to their corresponding targets. These functions are defined by parameters theta, which the optimizer adjusts during training. The choice of model class influences the flexibility and capacity of our model to learn from the data. Altogether, these components, objective function, optimizer, and model class, form the core framework of supervised learning. They work in concert to produce models that can make accurate predictions by systematically minimizing errors and selecting the best possible functions within our set. Now, let's look at how our supervised learning model performs in fitting and evaluation. First, on the training set, the mean squared error, or MSE, is approximately 1118.22. This gives us an idea of how well our model is capturing the patterns in the data it learned from. A lower MSE indicates better performance, but it's important to compare this to how it does on new data. Moving on to the test set, the MSE is about 667.81. Notice that this is significantly lower than the training error, which suggests our model generalizes quite well to new patients. It's doing a good job at predicting unseen data, which is exactly what we want. To put this into perspective, let's consider the random baseline. When predictions are made randomly, the MSE jumps to roughly 15,887.97. That's a huge difference, demonstrating that our model's predictions are far better than chance. It confirms that the model is learning meaningful patterns rather than just noise. Finally, a quick note on the dataset size. The model was trained on data from 20 patients and tested on 3 new patients. This small but targeted sample helps us evaluate how well the model might perform in real-world scenarios where data can be limited. Overall, these results highlight the importance of evaluating both training and test performance, and they reinforce the value of our model's ability to generalize effectively.